Finally, I come to the second part of my talk. It will be much shorter than the first part because we already have all necessary ingredients, and I just have to explain how all this is related to Schubert calculus. So let me remind you what is the main idea of Schubert calculus. So to solve enumerative problems about lines, planes, subspaces, and so on, we consider the flag variety, which can be defined for any connected reductive group as a quotient space of this group by a barrel subgroup. So this quotient is called complete flag variety, and in the case when G is the general linear group, this flag variety can be indeed identified with the variety of flags in Cn. So a flag is a sequence of subspaces, and a flag is complete if there are no gaps in this sequence. So the next subspace has dimension 1 greater than the previous subspace. So we will consider two main examples. The first is of type A, when G is GLN plus 1 over complex numbers, and then B is just a subgroup of upper triangular matrices. And the second example is symplectic group of even in the space of even dimension, and we choose non-degenerate skew symmetric form so that the barrel subgroup again can be realized by upper triangular matrices. What is interesting about flag variety is that it can be represented as a projective line fibration in n different ways. And this is a very special property. And I think there is a theorem due to Yaroslav Vishnevsky that under certain assumptions, a flag variety is a unique variety with such property. So how to get these projective line fibrations? We have to consider minimal parabolic subgroups. These are subgroups which are just slightly bigger than the barrel subgroup. For instance, in the case of GLN plus 1, we should take the subgroup which consists of almost upper triangular matrices, namely we allow a single element just below the diagonal to be non-zero. And of course there are n ways to choose such an element, so we will have n minimal parabolic subgroups. And it is easy to check that the variety G mod Pi is dimension 1 smaller than G mod B, and of course there is a natural projection, and the fibers of this projection are projective lines. So we get n different structures of projective line fibrations, and this means that we get n different push-pull operators. In Schubert calculus, these operators are usually called divided difference operators. In short, everything in Schubert calculus can be described using these push-pull operators. There is a special basis of Schubert cycles and in the Chow ring of G mod B, and it can be constructed explicitly using push-pull operators. So the main message here is that to understand Schubert calculus, we have to understand the action of push-pull operators on the Chow ring of G mod B. The next ingredient that I need is a Gelfand-Zetlin polytope, and these polytopes can be defined in various types. Classically, they were defined in representation theory using special bases in representations of classical groups. I will be only interested in types A and C. So to define these polytopes, we first define so-called Gelfand-Zetlin patterns. Type A pattern is on the left, and type C pattern is on the right. So here I took explicit examples for n equal to 6 in type A and n equal to 4 in type C. And in general, the polytope will live in the space of dimension D, where D is n times n plus 1 in case of type A. So D is a triangular number, and it's clear from this Gelfand-Zetlin pattern that it indeed has triangular number of cells. And in type C, D will be equal to n squared, so it's a square number. It is not so clear from this pattern, but you might notice that if you arrange these cells, like you count together cells in consecutive rows, then you will get odd numbers, and it is well known that the sum of odd numbers is equal to a square number. And every polytope is defined by 2D inequalities, namely a coordinate in each cell is between its left upper neighbor and right upper neighbor. So we have 2D inequalities, and in general these polytopes are not simple. What is interesting is that each polytope can be represented as the Cayley sum of two facets, namely consider the facet pi given by equation xi is equal to lambda I. So I label coordinates in the first row by x1, x2, so on, xn. And qi is the facet given by equation xi is equal to lambda I plus 1. And then it is evident from definition that Gelfand-Zetlin polytope in each type is the Cayley sum of pi and qi up to a parallel translation. And on the left, there is a familiar example. And now I might tell you the true nature of this polytope. So it's a Gelfand-Zetlin polytope for in type A for n equal to 2. And in general, we will have n mitosis operations because there are n ways to represent the Gelfand-Zetlin polytope as the Cayley sum of two polytopes. Another important point is what is the vertex V. So the definition of geometric mitosis dependent on the choice of a vertex V. And here there is a natural choice, namely there is a so-called Kogan vertex. And traditionally Kogan faces of these polytopes play important role in Schubert calculus, and Kogan vertex is given by equations x1 is equal to lambda 1, x2 is equal to lambda 2, and every coordinate is equal to its left upper neighbor. This is in type A. In type C, this is more intricate, namely in the first row we again have equations pointing to northwest, but in even rows we have equations pointing to northeast. So we have kind of zigzag paths here. And this definition of Kogan vertex is from Fujita's paper. So we get n mitosis operators. In particular, in this example, in type A2, it is clear that we have two ways to represent this polytope as the Cayley sum. One way we already considered, and there is another way using faces P2 and Q2. There is also a purely combinatorial part in this story, which preceded this convex geometric part with Gelfand-Zetlin polytopes in type A. Namely, Knudsen and Miller originally defined the mitosis on so-called pipe dreams. These are tables of such triangular shape filled with pluses. They have interesting meaning related to permutations, but I will not talk about this. These are quite well-known combinatorial objects, well studied. They were introduced, I think, already in the last century by Fomin and Kirillov, who proved certain positivity result about Schubert polynomials. So there is a purely combinatorial operation on these pipe dreams, and pipe dreams in pipe dreams in type C have different shape. They're called skew pipe dreams, and again they're considered in Fujita's paper. For skew pipe dreams, it is clear that the number of cells in them is also a square number, because here you evidently see that it splits into a sum of successive odd numbers. So I don't have time to remind combinatorial definition of mitosis. It is a simple combinatorial rule, and it can be found in the original paper of Ezra Miller in its pure combinatorial form. What is important here is that pipe dreams are in natural projections with faces of Gelfand-Zetlin polytopes. Not with all faces, but with those faces that do contain the Kogan vertex. And such faces are called Kogan faces. So combinatorial mitosis can be formally extended to an operation on faces of Gelfand-Zetlin polytopes. And it turns out that this operation has geometric meaning in terms of Pukhlikov-Khovansky rings. So let me write down just a single example of combinatorial mitosis, though I haven't given a definition, because this is exactly the example which we already considered in convex geometric setting, namely in type A2, we get three-dimensional polytopes, which we already considered, and there is only one non-trivial case of mitosis, namely the case when we get not just one offspring or no offspring, but two offsprings. And in this case, the combinatorial counterpart of this operation looks like this. So we have a table with two pluses, and it gives two offsprings with one plus. It was already known that this combinatorial mitosis can be interpreted as push-pull operators. And what is new is that the same combinatorial mitosis can also be interpreted using geometric mitosis. So let me summarize the main connections between all these ingredients. First of all, the Chow ring of the complete flag variety is isomorphic to the Pukhlikov-Khovansky ring of the Gelfand-Zetlin polytope. And this is true in all types. This result is due to Kummer's caveat, and it's a very well-known result. Next, if we consider push-pull operators as operators on the Chow ring, then they produce operators on the Pukhlikov-Khovansky ring, and it turns out that the convex geometric mitosis yields the same operators. So if we identify elements of Pukhlikov-Khovansky ring with linear combination of faces, then we will get the same operation. This is true in type A, this is I checked, and it seems that it is true in type C, but this relies on certain correspondence between Fujita mitosis and its simplified version in type C, which has to be proven. So I have not proved it yet. So in type A this is true, and in type C this is conjectural. Also, this convex geometric mitosis, if we translate its geometric definition into combinatorial terms in terms of pipe dreams instead of Kogan faces, then we will get exactly mitosis of Knudsen-Miller in type A, and again conjecture mitosis of Fujita in type C. Finally, there is an interesting question: what goes on in type D? Because combinatorics in type D is quite different from combinatorics in type A and C. So that there are also Gelfand-Zetlin patterns, but they look different. Gelfand-Zetlin patterns in type B, they look the same as in type C, so combinatorics is the same. But in type D, it's different. So my hope is that geometric mitosis can be used to produce a new combinatorial rule in type D. And these results are partially based on my paper push-pull operators on convex polytopes, and I am also working on a preprint on simple geometric mitosis, which will appear soon. Thank you for your attention.